Good. I want to welcome all of you right here and also all the family and friends watching us live from their homes to the final project presentation of DroGone. We want to kick things off with a short introductory movie, so please enjoy.
Drones have grown in popularity in recent years and continue to revolutionize industries like cinematography and photography. Unfortunately, they're also being exploited. Drug smuggling, grounded airports, and intrusions of prohibited airspaces are just a few of many cases where drones are posing an inconvenience or even a threat to public safety. At DroGone, we developed an autonomous solution that disposes of an unwanted drone and delivers it to a safe location without harming anyone in the process. Today, we proudly present to you Peregrine, our autonomous drone-catching drone.
And on that note, I want to thank all of you in the name of the whole DroGone team for attending this very precious moment of ours, and also for your support throughout the last year, in the form of funds from some of you, or also through coaching and expertise from others. It is safe to say that we wouldn't be standing here in front of you right now if it were not for your patience and also your wisdom. We want to start today with a short overview of the last year of our journey to this moment right now, before we dive deeper into the intricacies of our system. It all started in the September of the last year, when the team sat down for the first time to talk about this upcoming project. And we were presented with the uprising problem of illicit drones intruding private or potentially dangerous airspace, and we were told that local authorities at the current moment had no means to remedy this problem because there was no adequate commercially available solution. So the team quickly fixated the project vision. We wanted to catch and escort an illicit UAV to a safe predefined location and do this as autonomous as possible. In the following weeks, we did some brainstorming and we came up with a lot of different design ideas which coalesced into our final project approach of a carrier drone with a top-mounted catching mechanism, as you see right here. Then, in the November of the first semester, our hardware team was already able to assemble our first prototype called Sparrow and combine it with our first proof of concept of our catching mechanism. This was the basis of all future iterations of our system, and we were able to present it at our first intermediate review, where actually some of you already attended and gave us some valuable feedback which we could later then implement. Then a long time passed, and near the beginning of the second half of the project, the hardware team was able to assemble our second prototype, Red Sparrow, with all these changes and also amplifications in mind. We were then able to thoroughly test our second prototype, for example, in a wind tunnel. All this while, the software team was working towards the Mohammed bin Zayed International Robotics Challenge alongside the ASL and the RSL to compete against other prestigious universities in Abu Dhabi in February early this year. The MBZIRC is a biannual challenge that poses different challenges, three exactly, which are derived from real-world problems. We were able to compete in the first of these challenges, which was actually catered towards our use case, intruding drones. We were able to learn a lot from the ASL in particular about autonomous drone control, even though the competition didn't quite go as planned. Then shortly after we returned from Abu Dhabi in March, we were forced, for obvious reasons, to work from self-isolation in our home office, but this didn't stop us from continuing our work towards our project goal. So we further designed our hardware, we ordered some parts, and we also built a robust simulation to check all of our software modules. This hard work then paid off in May of this year when we were able to finally assemble our third and final iteration of our prototype called Peregrine, and also mount our final catching mechanism design on top of it. We were also able to adapt a lot of the code we used for the MB-Circ and even port some parts one-to-one to our new system, and we're then able to make our first autonomous catch attempts in June of this year. And since then, we've been ever trying to better our system and to make it even more robust. And that brings us here right now, where we are able to present to you our final configuration of DroGone.
With this, let's have a look at Peregrine, and let's maybe start with one of its most prominent features, the catching mechanism, or spiderweb as I like to call it. And as Michael said, the idea of having a catching net originated in the beginning of last semester and was thoroughly tested first, where we saw that this method works particularly well since drones really like to get entangled in this thin net here. However, we also saw that this net isn't very strong and may break on some impacts, as you can see here, which led to this double design we've adapted here. On the bottom, we have very strong Dyneema strings with a break force of 1000 newtons. These are here to absorb the impact, whereas the thin net here on top of it is there to entangle the drone and keep it in the net. We've actually never lost a drone once it got entangled in the net. Everything is held up and stretched out by these 6 custom designed carbon fiber arms. These are designed to optimally feather and dampen the impact. To find this design, we did a lot of FEM analysis, and then after manufacturing, we also validated and verified this design before then mounting it on the drone. In the middle, everything is connected to our custom designed dome, which is actually very lightweight, but also strong enough for a person to stand on top of it. And this dome sits on a foam ring here on the bottom, and both of them are sandwiched together between 2 carbon fiber plates on top and on the bottom, which are, I don't know if you can see this, which are attached via strings on the inside of the dome. And this allows the dome to act rigidly if an impact happens on the outside of the net and pulls on it, but the dome gives in softly to an impact directly on the dome, so we got both cases covered. The dome is there to obviously protect and house our sensors, namely a color camera and a thermal camera, which are currently mounted on the drone, and also to give them a field of view clear of any net or anything that might obscure it. Okay, so let's have a look at the rest of the drone. Peregrine clocks in at 6.7 kilograms. That's 1.7 kilograms heavier than originally anticipated. We have mounted a high-precision RTK GPS system on the drone, which you can see here in the back, and this allows us to position our drone in the sky with centimeter accuracy. We estimate its current value with everything attached on the drone, with the sensors and everything attached, to about 9,000 francs. Its 6 MAD 400 motors produce a combined thrust of 130 newtons. That's about enough to lift 3 cats. And this gives us a thrust to weight ratio of 2, a little lower than the 2.5 we originally anticipated. However, with this, we're still able to achieve a top speed of over 65 kilometers per hour in under 3.6 seconds, which is an acceleration comparable to a BMW 3 Series, or about twice as much as your typical consumer drone like a DJI Mavic. When comparing to a Mavic, we can also look at the vertical acceleration and speed. We got a vertical acceleration of 9 meters per second squared and a vertical speed of about 45 kilometers per hour. And this also easily outperforms typical consumer drones, as you can see here in this short video. We're quite a bit faster there too. So you can imagine that these motors pull quite a bit of power. So these motors burn through 2 of these 5,000 milliampere hour batteries in about 5 minutes when in dynamic flight or 9 minutes when hovering. That's what we originally anticipated, more or less. But that's enough for our cost to catch a drone and return it. It gives us a range of about 1 to 2 kilometers. However, right now we're still limited by our network to about 200 meters, but this could still be improved upon. One final thing, one issue with large hexacopters is that they get very undynamic, and one thing we did to improve this, especially the yaw behavior, is we actually tilted our motors by a few degrees. And this has drastically improved our yaw behavior, and we'll show that to you later in the prototype evaluation. This makes the drone in total act much more dynamic and better to control. Okay, so let's come to the end and let's have a look at the brain of our drone here, the Intel NUC, which runs all of our custom-made software, which is what Nasib's going to talk to you about now.
Yes, so as Johnny mentioned, our onboard computer runs our in-house developed software. Here you can see the entire software architecture that's running on it at the moment. The modules we mostly focused on and developed during these last 2 semesters were the detector, tracker, motion planner, finite state machine, and graphical user interface, as well as integrating a high-level controller such as the nonlinear MPC. Now let's begin with our autonomy pipeline. That's the detector. So our sensor of choice here was a thermal camera because it seems to pick up the image of a drone quite well. What we get from the thermal camera is an image that looks like this. We then perform canny edge detection on this image and perform second-order hue analysis and compare that to a reference object, which we already know is a drone. If we get a match, we then have a detection and can read out a positional measurement of where the drone is relative to the camera frame. In real time, this looks something like this. Here on the left, we have raw thermal cam images, and on the right, we have the detections running. And at the top, you can see that the distance underlined with red is the distance estimated in optical Z direction, which is actually the hardest element of the detection or the measurement process here, because we basically need to assume the size of the drone that we're trying to detect, and then based on its size in the image plane, we can then determine how far away from us it is. These measurements are then passed on to a tracker. In the same time, the tracker is actually predicting the state of our target drone using the predefined motion models that we assume the drone is flying with. Using this predicted state called the a priori and the measurement, we can then fuse the two to get an optimal, which is called the a posteriori, and this is the actual target location or the most likely target location. In this entire process, we also determine what motion model is most likely. Since we don't know exactly if our drone will be flying in a straight line or will be stationary or accelerating, we need to figure out what's more accurate. And once we have the motion model that fits best, we can propagate it into the future, getting 20 points into the future, which we can then pass on to the motion planner. The motion planner, first, before it can even start planning catch trajectory, needs to place itself vertically beneath the target drone. Once it places itself vertically beneath the target drone, it actually plans interception trajectories to each of these future predicted states of our target drone, and then optimizes using Dijkstra's algorithm for time and jerk. Jerk is just a change in acceleration. Once we have determined which path is optimal, we can actually fly and intercept the drone. To fly these trajectories, we need something that converts the trajectory into concrete motor thrust commands, and that's why we have the nonlinear MPC. The nonlinear MPC takes the trajectory we want to fly, converts it into a roll, pitch, yaw, rate, thrust command, which is then interpreted by the low-level PID as concrete motor commands. Now, behind this entire process, we need something to coordinate, and that's where the finite state machine comes into play, or as I like to think of it, the brain of our system. Here we can see at the top the communication flow of the finite state machine with various modules, and below you see the state graph of the finite state machine. So we begin in search mode, where a manual operator flies the drone close enough to the target drone so that we can actually start seeing it in our picture. Once the detector gets 3 consecutive detections of the same target, it lets the finite state machine know that now that it has done so, and we are actually detecting the correct target. The finite state machine then proceeds to tell the tracker that it can now begin tracking the correct target. And once the tracker outputs a good enough state estimate of our target, the motion planner can begin planning its motion towards the target. Once the motion planner is actually close enough to the target drone that we can attempt to catch, it lets the finite state machine know that it's going to now fly a catch trajectory. This entire process, while it's flying the catch trajectory, the finite state machine is still listening to the tracker and detector to check whether everything is still in check. And if the MPC issues a higher thrust command just for hovering, that means we actually have caught the drone and therefore can enter land mode, which is then passed on to the motion planner who plans our landing trajectory. Now, we wanted the human operator to remain in the loop during this entire process, so we actually developed a graphic user interface just for this. The graphic user interface looks like this. It has all the relevant information at a glance, so the operator can know that the system is healthy and running smoothly. Now, at the top left, we see that there's a start autonomous operation button. This is actually where we transition from manual mode to autonomous mode. At the bottom, we see the plots of Z position, X and Y position. Here we plot the actual position of our own drone, the target drone, as well as the trajectory we're trying to fly. During this process, we're also able to abort the mission in case we do deem the situation to be too risky to follow through with. So the human always has the last call on whether or not our system should pursue a catch or not. A lot of these modules had to be developed in simulation beforehand so we could isolate them and test various components. We also managed to integrate the entire pipeline besides the detection module in simulation. Here, instead of having the detection module running, we actually implemented another solution. What we did is we took the ground truth of our target and processed that with noise. We processed it in a way to simulate camera behavior, so our noise was mostly added in optical Z direction, whereas X and Y was relatively certain and precise. This was actually something we used further to develop the rest of the pipeline outdoors, and Michael will tell you now more about this.
All right, let's come to the testing pipeline right now. So there was one major adaptation that had to be done concerning our outdoor tests. And this adaptation was in the detector, or more precisely in our sensorial system. We were unfortunately not able to implement the originally planned radar camera fusion system, which we also presented at the intermediate reviews. And we also didn't have the time to implement our own camera-based detection system, even though it showed great promise, as you have just previously seen. So what we did is we implemented a target real-time kinematic GPS system on our target drone in the outdoor tests, and we used the same post-processing that Nasib just told you to simulate these detections so that we are still able to test all the other modules for their autonomous behavior. For that, we had to custom design this 3D printed mount to be able to implement or put all the necessary modules of the RTK system onto our target drone. All right, let's get to the tests that we conducted. We decided to split up our final project goal into these 10 steps, these 10 milestones, to tackle them as modular as possible, because we realized that autonomous drone control is really difficult. And we first wanted to test our hardware system and wanted to verify our design choices and also our production quality of our final prototype. So the first 4 tests were catered solely at our hardware and were all conducted manually. So these were all manual tests. If we then were able to verify that our hardware is in principle able to catch another drone, we would then move on to the further tests and check our autonomous pipeline and our algorithmic structure to see if our written code is actually able to achieve the same, or in the best case even more, than an average human pilot. And how turned that out? You see that in the beginning with the manual tests we were able to have some stationary and also some catches with a linear moving target, but we then quickly realized that it was not really feasible to catch a circular or even a freely moving target, because it was really hard to actually catch a drone manually with our system. This wasn't actually too bad, because our hypothesis at the beginning of the project was that it would be better to use an autonomous system, so it was actually at the time quite nice to see that it was really hard to catch it manually. So we didn't even attempt the freely moving target after failing the circular moving target. We then went on with the autonomous test, and we were able to autonomously, with the testing pipeline that I just mentioned, catch a static target and also a linear moving target. We were also able to verify that our algorithmic structure was able to catch a circular and a freely moving target, but only in simulation. We were not able to test that outdoors. We also wanted to focus on the static and linear catch, so that we would also be able to show that to you today, hopefully. We also kind of abandoned our final original goal, because we imagined our system to be able to dynamically switch from the manual to this autonomous mode. So we wanted to incorporate the systems such that the manual controller could fly towards the enemy drone, and as soon as enough detections were there, automatically switch and then go to this autonomous catch. But we didn't really want to dilute our attention in this semester, and we really wanted to focus on the autonomous catch itself. I want to emphasize once again that all these autonomous tests were done without our vision system implemented due to the aforementioned problems, but we are still really proud to be able to show to you that our system can autonomously catch another drone as long as it is fed the target position, irrespective of its source. So that of course opens up a lot of possible follow-up projects into which Nasi will go into further detail.
Yeah, but before we go into the follow-up projects, let's talk a little bit about finances. So our total budget consisted roughly about 55,000 francs. We spent an estimated 35,000. However, with all the transport costs now, we probably spent more, around 36,500 francs, sorry. That leaves us with a residual of 19,000 francs, with which we could actually do a lot of follow-up projects and continue to progress our own prototyping system. Now, something that we have been looking at is actually drone detection and measuring the distance and the position of the drone using neural networks. The idea behind this would be to basically take the color cam image, maybe even fuse the color cam image with the infrared image from the thermal camera, and then let it pass through a pre-trained neural network, maybe the YOLO V3 network, which is actually optimized for real-time object detection, and then evaluating whether or not there is a drone in this picture. Now, for this, we actually have set up the optimal pipeline for labeling our own data automatically, because we do have the ground truth of our target drone, and we do have the ground truth of our own drone. That way we can map it back and map it into the image plane, and actually label the segment that is the drone in our image. Another option would be to look into other camera systems or other radar systems for our drone in order to facilitate the detection and actually get more accurate and precise measurements of where the drone is. Now, here comes in question, for example, the radar camera fusion system that we evaluated last semester and the beginning of this semester. However, unfortunately, we were not able to implement it on our own drone. Maybe this could be something that we do in the future. In terms of hardware, when we first initially started this project, our prerequisites were slightly different. We optimized our drone to catch DJI Phantom drones, which weigh around 1.5 kilograms, have a diameter of 55 centimeters, and a top speed of 50 kilometers per hour. However, we see industry moving into more compact forms. The DJI Mavic 2, the DJI Mavic Air 2 are all getting smaller and smaller. That means actually we need to become more dynamic and less robust as a system to catch these drones better and faster. Now with that, I'd like to conclude this presentation. I'd like to give a big thank you to our team here who spent the last 2 semesters really working very hard on this project. And now we'll have time for questions, followed by a live demonstration and a short break in between the two. For all the people watching us over the live stream, we hope to also stream the live demonstration, and we're excited to show you what we've done. Thank you.
Yeah, so first of all,
Please.
impressive, wonderful results,
Thank you.
especially also with these limitations you had, physics in the lab in the last couple of months. So you have shown that with linear movement and static charge, you can do a good job. Now with more dynamic movement, it's difficult, and you mentioned also that it's very difficult for a pilot. Did you also consider or try to have first-person view control for doing this? Because, I could imagine that this is probably easier, or at least if it's possible, it's only possible.
Yeah, we tried it. We had FPV camera mounted on the drone. We had it mounted at different angles. We also tried a 3D camera and having it on a head tracker to be able to move around. However, all of these options were not making it very easy or more like difficult, since the angle to catch the drone is more up than what you typically fly at, and overall all the catches we actually did were without the FPV system in place, because it made it harder actually than we thought.
I think we also have to mention that that of course we were not trained drone racing pilots. For example, this was maybe an option we could have explored more to use an FPV camera and also a trained pilot. Yeah, but we catered the product to be more self-sustaining, not needing a really good pilot to pilot it.
Yes, congratulations for the great work. I was wondering how many pixels do you need in order to be able to detect the drone?
Ian
Maybe I can answer that. It depends. Right now we set the limit to an area of about 20 to 25 pixels on the server cam, which has a low resolution. But it is possible to detect it with less pixels, but the arms are not visible on the image. So an option would be to take the information from the tracker, the predicted state, and if it is close to that predicted state, we need less details to say it is a drone. But for the first detection, we need about 40 pixels area.
So the answer was that we need about 40 pixels.
So the maximum distance is about 20 meters for a first detection with a resolution of about 640 by 300 something pixels. Of course, the color cam has a lot of better resolution, so we could also use that for a first detection.
Yes, please.
I have a related question to what Harry asked before. How do you get distance to the drone? Because you have always the estimate of...
Yeah. Okay, the question was, well, how we do get distance.
Right now we use the information that we know which drone is flying in the air and we know how big it is. So we get the radius of the minimum enclosing circle, and then because we know the real distance, we know the focal length and the distance in the size in pixels of the drone, we can do an equation and calculate the distance. Of course, this depends also on the angle the other drone is flying. So if it is accelerating and tilting a lot, the area gets smaller, so we detect it farther away. But and we need to know what drone it is. That's still a limitation we have.
Do you have any estimate how accurate you can do this? Because that to me sounds like it's going to be way on what it actually is. Because you have only few pixels that are a drone, and then you have to...
Actually, it's accurate enough. If the drone flies at about 12-meter altitude above our drone, we get plus minus 70 centimeters in distance. And of course, the closer we get, the more exact it gets. So during approach, we get more and more exact measurements, so we can replan our trajectory.
answering questions here.
Any more questions?
Yes?
Maybe a follow-up to Ron's question. So the manual attempts, if you had to guess, was it more because you weren't good enough pilots? So if you had, for example, a trained drone racing pilot, he could have maybe caught the moving drone? Or was it because the system is not agile enough?
The question was whether the manual catches were not possible due to the system not being agile enough or the pilot. And I think it's the pilot's error, definitely. So I was flying these tests, and the problem that you have as a pilot is it's really difficult to estimate the distance. It's the same problem a camera has, since you just have the size of the object to work from to estimate the distance, and also the distance to the target. And if that is not aligned and if that is moving freely, that is really difficult, especially if it gets further away. So a system that estimates the position is quite helpful. Yes?
Just an understanding question. What's the distance of the final catch? How close are you to the target drone?
So we start searching for an optimal... Sorry. The question was, what distance do we have to be at for an actual catch trajectory? And we start actually, this is a variable that we started tuning with a little bit and trying to figure out experimentally which one matched best. But we realized that around 3 meter distance, we can quickly calculate a trajectory that can help us catch the target. So we actually have, I said we place ourselves vertically beneath the target drone, but we actually have 2 follow modes. The first one really does try to place itself just in the XY plane straight beneath, so the projection of the target drone straight beneath there. But then in the second follow mode, we actually move upwards as well in Z direction and get closer to the drone. And then what should happen is that smoothly, while we're also moving forwards, we get close enough to calculate an optimal catch trajectory that we can then fly. And then we have certain criteria that need to be met for us to really say, hey, this is a good trajectory to fly or not.
3 meters plus minus.
Yeah, 3 meters plus minus. Yeah, correct. Yeah. Unfortunately, 4 days ago, we had a rough crash that did require us to rebuild most of the drone, but we were very close to catching a drone that was moving around 3 meters per second. But then we didn't have enough space to actually continue the flight and had to manually take over, but then our pilot made a slight error, and unfortunately, it ended in a crash. But I do think we could have caught that drone. The best thing we've reached till now was around 1.5 to 2 meters per second. Yes?
So you have now the vision-based detection mechanism that you showcased as a drone, but you don't have it together.
Yeah, correct.
What is the main reason that you did not manage to make this, at least in a simple setup of having a stationary drone and catch that, but with the camera and not without it?
So we were very close to doing it, but then we had a few issues with drivers and bugs, as usual, with ROS and robotics. But then basically what happened was that we would have MAV-ROS running, and then as soon as we would launch our thermal grabber for the thermal camera, it would actually crash MAV-ROS, and then we couldn't fly our drone anymore. And we couldn't figure out, we just didn't have enough time to figure out what the actual problem is. Additionally, we didn't really make our detections very robust against outliers. So if we do get an outlier detection, our tracker then starts having a hard time. Yeah.
And now you're figuring out the driver crashes.
Yeah.
6 months later, and you know what read running. So
Yeah.
did you switch, or what was it?
It was just a matter of slight misplanning, unfortunately. We tried these things out much too late. We should have tried sooner, and then we would have had enough time. But the thermal camera, we would just been trying out on its own without running the other things in the modules separately and trying to optimize it that way. And we only put it onto the drone very late. So we did that maybe a week and a half ago, 2 weeks ago. And yeah, and we also, in the first semester we were flying with the Volero, we only have had this drone for a month and a half now. Yes?
Looking back now, how far could you have
I think Corona had its upsides as well, because requiring us to also work from isolation really made us emphasize to our work on the simulation and our separate modules. And I think many of us also managed to work maybe even more productively in simulation, while sometimes, communication was lacking, or you just had to make do with Zoom and start in the morning, go all the way on till night. But I think in the end, it also had its positive effects. I think the only downside was really the testing of the entire system, that we were only able to do that at a very late stage. And had we had maybe 1 or 2 weeks more, I think we would have had the entire pipeline running. Maybe for static catches only, but maybe not for linear. Yeah.
Or at least we would have tested it.
Yeah, we would have tested it thoroughly. But I'm confident we would have managed. Yes?
You said for the manual intercept, the main challenge is the perception. So I'm just curious, what's the main challenge when doing it autonomously? Is it the planning, so the update rate, or also perception?
Yeah, there are a lot of things we didn't realize when we started, but you really need to have a well-integrated system. So what we realize is that you need to really tune the motion planner together with the controller. Then the other part was detections. That, I think, was one of the hardest things we had to do, because the sensor systems are just not on the market to really make a job like this very easy. And other than that, it was just really mostly the integration of all those different modules that was the hardest part in general. Not a module separately, but really the integration of all of them. Yeah.
What the financing question.
Yeah.
What would you do differently? So you had to decide once for the concept and everything. Would you do it totally different, or is it a rare track just to?
I think we're happy with the general concept of having a drone to actually catch other drones. We would not now try and implement a sort of ray gun or jamming system instead. I think what we would have done was maybe reiterate our actual specifications for our own drone and try to make it more dynamic, maybe a bit more compact and lightweight. Other than that, I'm not sure if...
Yeah, I think one thing we would definitely profit from would be the whole testing structure we established now, that we got more productive when testing, and I think that was definitely allow us to progress faster in the beginning. But aside, I think the requirements and the way we've tackled and also made our decisions was quite clear, and we know why we built the system the way we did, and I think we would do it the same way again today. Yeah. Maybe we would give it a spider name and not a bird name.
Yeah, actually more fitting. I also think the main point would be with the testing pipeline, or more precisely with the simulations, because this was a big point that we learned a bit the hard way. I mean, we were really naive in the beginning, of course. We had no experience with drone control, not even to mention autonomous drone control. So a lot of the times we really went testing in the first semester. We just ran our code. We thought it would work naturally. And it took some crashes and some unexpected behavior until we realized that a good simulation that proves your system beforehand was really something that you had to ensure. And it really helped in the second semester. But I think if we would know that now from the beginning, this would also quite help accelerate the process.
Yeah, I think we definitely learned that code that hasn't been tested is definitely not working. Yes, I think that was a very good decision on our part, because it did push us to make a lot of progress in the first semester and really make us step on the gas and throttle at the beginning. Had we not had that competition to work towards, we would have not seen a lot of issues until very late. For example, also realizing the potential or the value of a simulation, because we implemented our simulation to adapt our software for MBZerk in maybe 2 weeks before MBZerk. So before that, we were testing in the Viken day and night. But
not really productively.
Not always productively. Yeah. But yeah. Anyways, I think if that's the last question.
Do we have some questions in the live stream or no?
No? Then we can start moving towards the area where we'll have the live demonstrations. There we'll also have some snacks and refreshments. And feel free to ask us questions on the way too. Thank you. Johnny. All right, so now we'll fly up the DJI that we'll catch. That's going to be our target. Johnny's going to align himself with the DJI or the target drone just to make it easier for himself to actually catch it, since it's otherwise quite rough to place it in the sky if you're not standing right behind it when you're flying. So Johnny's arming now. Just give us a second. Nein, Lukas. Lass es bitte. Wir wollen es ja vorzeigen.
Ja.
Entschuldigung.
Nein, easy. Ich habe einfach schnell ein Bild gemacht.
The drone is killed. The props won't spin. You guys can come closer, take a look. Check out the catching mechanism, the arms, the net, how the props have been entangled in the net itself. Now, as you can see, like the net itself even cuts through the DJI props, which is, I think, a plus. And it has a hard time getting out of the net. You guys can try it out here. Push a little down. Check out the arms. Here we see the camera system. We actually covered our thermal camera because it is the most expensive hardware on this drone.
How much does it cost?
With thermal grabber, it's 5,000. Without, just the camera is 4,000 francs.
So actually more than half of the price point.
Yeah. And then here we have the RTK system at the back, which is just a high precision GPS, essentially. Yeah.
But usually there's a window on it, right? You should be covered.
Yes, at first we had planned to have a plexiglass screen at the top, but then actually we constructed or reconstructed our camera guard or mount there, so we decided to remove it. And also when we're running the thermal camera, not ideal. Unfortunately, no. No. So now we're gonna take out the DJI, get ready for an autonomous catch. We need a little bit of time to prepare for everything, but we'll get the go-ahead from Felix when they're ready. Now, otherwise we can also go back there and take a look at the posters we have set up. Maybe we can take a look at some videos of our other autonomous catches. I'd like to ask Johnny, go to the computer, please. Thank you. Okay. So yeah, if everyone has had a chance to check out the net and everything, it's a little less tense than it used to be.
These are already cut.
Yeah.
Propellers.
Yeah, they're. So you have to actually swap. Takes like half an hour, but we could redesign this to make it quicker. Yeah.
Did you buy the net?
We buy just the net, and then we have this dynamo string. Dynamo string, correct. I'm not part of the hardware team. Sorry. Yeah, and this is to absorb the impact here. Yeah, it does flex quite a bit.
Where is this extra 1.7 kilo comes in?
I think mostly from the cameras. The cameras itself with the mount, they're 700 grams. They're quite heavy, and then.
You probably have included a camera in your pre-calculation, no?
I mean, it did change a lot with time. So at the beginning, we didn't even know we were going to mount 2 cameras. We didn't really figure out what sensors we wanted to have on at the end, and that kind of changed. Housing is also quite heavy. This could be re-engineered to be lighter.
I think Lucas, 500?
500 grams, yeah. The dome is SLA printed. Right. I think so. And then we have, I mean, the carbon is quite light. Yeah. So,
What are those strings for?
these are, as Johnny mentioned, to make it rigid for when it's pulled on the dome. But then we still have the foam underneath so we can absorb impact. But we prefer not to push down too hard because when it's on the ground, the legs do tend to break quite easily, unfortunately.
It's actually a good safety measure. Most of the crashes, only our legs break.
Yeah.
Yeah.
Yeah, the legs.
They are
Yeah.
This is good if you have a defined place where it should be.
Yeah. So now here we also see the tilted props. Always
All of them are tilted, right?
swapping it. No, all of them are tilted. This allows us for better yaw and more dynamic flight. Okay, so let's maybe move back to the safety zone. Yeah. So we'll ask everyone to go behind the tables. Können wir gerne auch zeigen. Setup-Video, Linear Catches möchte ich gerne zeigen.
Das sind Dynamic Catches. Again or as?
So yeah, we need to do a lot of pre-flight checks before we start flying with the autonomy pipeline. Make sure everything is running smoothly. We don't want any accidents today. We haven't had any yet, so let's keep it that way. I'll get the go-ahead from the two over there when they're ready. Other than that, we could also take a look here at a video of some other autonomous catches we've actually performed. They'll be running here in the background all the time, so please feel free to take a look. Du musst dich bewegen ein bisschen. So now we have mounted the RTK system onto the DJI drone, which is going to give the position measurements of the target drone. Where now the DJI has this quirk where you have to fly it up once to make sure it has its GPS location so that we can actually fly above 10 meters, otherwise we're limited. So we've done that, we're ready in that respect. So as you can see, there's also a designated landing area. There's an X marked on the floor. If everything goes to plan, which I think it will, we will land in that specific area. That'll be the landing trajectory that we send to, that plans to that point.
Did you guys get much opportunity to test here?
We've tested here only one day. One day we tested here. Yeah. Yeah. No. No. We tested before. We were always testing near Hängeberg or on the Hängeberg, and that was just because that was the best area we could find to actually have the flexibility to move around and not have anyone complain. Because yeah, not so easy otherwise. But it would be nice to have a bigger space to test. Definitely. Willst du den Bildschirm noch im Schatten stellen irgendwie? Du kannst das da ein bisschen bewegen, dann liegt das im Schatten. Okay, so now we're gonna fly up with the target drone. Make sure we have position measurements or so-called simulated detections. Yeah. So now what you're gonna see is Felix is gonna start up. We're gonna enter a hovering altitude where we'll then turn on our high-level controller and then enter autonomous mode. Don't worry about it. We've gotten the okay from Felix. Start autonomous operation. A rather centered catch right there. We are in land mode. Now we're going to land at that marked area right there. This is all happening without Felix touching any controls. So that's it. Felix, killed. Okay, you can go and take a look. Wait, leave the DJI on. Never mind. You guys can go take a look. The props are killed. The motors won't spin.
Nice one, man. Nice one. First autonomous sketch I fucking saw.
Smooth.
Soll ich den tragen?
Gerne. Ha? Ja, ja, wir haben noch.
Aber klar, für
Du musst dich ready stellen.
Für was? Ich brauche eine Drohne rein.
Ja, ja.
Wir müssen noch Kabel wegnehmen.
Okay, also zeig.
Da vorne hinstellen, dann können die Leute die da anschauen und dann könnt ihr schon mal anschauen.
Kannst du die Videos machen und er bereitet die Drohne vor?
We don't actually hear you.
Aber er muss die Drohne ja auch, muss den ja auch an den Screen anstecken. Oder haben wir noch einen zweiten Screen, wo es zeigen? Der ist noch drüben.
Ah, ist okay.
Do we want to record? Do we want to record? Do we want to record some, you know, user impressions? You want to go?
Oh yeah, let's. Am I still muted? No. All right. Hi guys, I'm back again. Let's have some interviews with the autonomy experts. Excuse me, sir. Oh no, wait. I know you. You're not very good at this. Let's go ask around for impressions. What did you think of the static autonomous catch?
It looks really fantastic and great.
Thank you. Thank you. First good feedback.
We didn't pay her. We did not pay.
Are you okay? Let me not interrupt this here. This is David. He's one of our coaches. Are you happy with the work we've performed?
Indeed, yes.
Yes?
Really great project.
That makes us very happy to hear.
And I mean, it worked.
Yes, thankfully. A few days
Never
ago,
doubted 1 second.
it wouldn't have looked this nice. Okay, now we have a real expert here. Michael Pantic, you've worked a lot with drones. What do you think of this? Is this
awesome.
a good engineer?
Nice, yeah.
Really?
Well engineered
I
drone?
like
Nice.
After the MB circuit.
This is some great confirmation.
There was
There was a lot of room for improvement. Yes, if you don't know, we participated in the Mohammed bin Zayed International Robotics Challenge. We did not perform very well. That was due to some issues that were out of our hands, such as state estimation, there was GPS interference. But it doesn't matter, we learned a lot and we achieved our goal in the end. And we're happy about this. Why?
Incredible work, man.
Thank you. What's your impression?
It was great.
The team's good looking.
Oh yes. Oh yes.
Alex, keep it in your pants. Okay. If you guys would like, you can now take a look at our graphic user interface on the laptop here in front. This is what an operator would actually be able to look at and control. Niemand ist interessiert. Bist gemutet oder nicht? Ja. Cheers.
That's impressive, bro.
Thanks.
I can't believe it fucking worked.
Me neither. I was sketched out when it went. In case you didn't hear, we are also showing the graphic user interface here beneath this canopy. You can come take a look. We have a screen recording of the actual catch now running. So this is our debug interface that we implemented just to make our lives a little easier. So here we see all the relevant information that we need to know before we start a test to make sure that nothing goes wrong. If everything here looks all right, then we can actually proceed. So now we see that the position of our actual drone is being plotted. Now we check back in the GUI. This is a screen recording of what we just did before. And now we also have a tool where we can record ROS bags easily. We can just give in a directory and the name we want to have for the file and start recording. This allows us to collect data sets and not forget, which we have done quite often. And we have to start it from the terminal.
Position mode.
Now we have changed in the MPC position mode and are getting ready to actually enter autonomous operation. Now you see that our drone has actually lifted and started hovering at roughly 3-meter altitude. Here we click at the top. Now we start at autonomous operation. And now it starts plotting the trajectories. Now we see the detections, the green line at the top. We're plotting the trajectories that we're trying to fly. And that's the catch trajectory that was actually sent in the end to intercept the drone. Now we'll hopefully see it change into land mode. We see on the left at the top, we have land mode. It sent the trajectory for a smooth landing, and we landed at the designated area.
Yeah, actually working is doing.
We went out of the blue is the target drone, and
The blue is the predicted estimate. No, not the reference of the MPC, but the predicted state of the target. So we look in like 2 seconds into the future, so that we have 20 points sampled at 0.1 seconds that the planner can actually plan to, and then you can pick one of the best ones to intercept it.
You have this also when you land, when you basically the target is...
Because our drone with this post-processor keeps running, we still get detections, and the tracker just keeps running then. But no one's listening to it anymore after we enter land mode. The motion planner just sends the final landing trajectory.
That's a legend.
Yeah, that's a legend.
Is it like normal that the detection is so shaky? Like
Yeah. So we simulated dropout as well. We didn't want to have just like perfect detection, so we say with a probability, I think the highest we've tested was like 0.3 to 0.4. We have a probability of dropout, so our detection is actually lost and we don't have a proper detection to work with.
But like,
And that's random.
now you were not simulating it.
Yeah, so what we did, we took the position with the RTK and then we processed that position.
Okay, because that's basically you're not doing detection.
Yeah, not here, not with the thermal cam, but we are simulating the detection. Oh, yes.
Okay, everyone. Thanks for tuning into our live stream. I hope you enjoyed. I hope you enjoyed our presentation and what you saw. And leave us a follow. We'll upload the like and subscribe. You know, we'll upload the video we had at the beginning of the final of the presentation. And yeah, I hope you enjoyed. And that's it from us. Bye bye.